All right, now for section 1.6, this is the last section of chapter 1 that we're going to go through. Um, Section 1.6 is talking about variation and the various applications associated with it. So we're talking about variation and applications. Let me jump into the notes to help explain this. A lot of times what happens is you'll be given a statement and you have to convert it into an equation. So it's kind of like math speak that requires a little bit of translation. You can think of it like being a translator of a foreign language. You're listening to something and then you have to change the language kind of in your brain and then communicate something differently. That's kind of the same idea here. So when we're dealing with variation, it's really actually pretty helpful in a lot of other degrees. So if anyone goes and you need to study statistics down the road, all of these concepts show up. They're huge. So anybody who's going to study, say, psychology, statistics is a huge part of understanding psychology, understanding kind of the way that people think and how they function, why they do what they do, their motivations. And a lot of that is driven by statistics. And so if any of you plan to study statistics in the future, in the medical community, anything like that, these are concepts that probably will show up at some point or another. Okay, so there's a few different things. We have direct variation. So the variable y is directly proportional to x if and only if y is equal to k times x. K is the constant of proportionality, or the variation constant is another term for it. It's going to show up in every single one of these problems. And the reason why, because the value for k is going to differ depending on the equation and the really just kind of some of the background stuff that you need. We'll go through some examples, so hopefully that makes a little bit more sense. Direct variation is the nth power. If y varies directly as the nth power, then you've got just x to the n with k multiplied in front. When you see the word inverse, you immediately think fraction, because that's really all it's happening, is you take your k and you divide it by x, or whatever variable that you're working with. So inverse variation is a fraction. Inverse variation is the nth power. It's the exact same thing as we had above. You're just replacing x in the denominator with x to the n. And they say here that n has to be greater than or equal to 0. Here's a question. Do you know why this is part of that definition? I'll give you a second to think about it. Okay. Here's why n has to be greater than 0. Because the properties of exponents state that if I have a negative exponent, that actually means that I can flip the location of it. So if, say for example, I've got a negative exponent in the denominator, I can literally flip it up to the numerator. So then it wouldn't be inverse variation, it would just be direct variation at that point. So that's why n, the exponent, has to be bigger than 0. Math, you're probably finding this out at this point, but math is a very, it is all about specific things. You cannot have just general ideas and how maybe this works like this. It's very, very specific in how it's set up. Joint variation, so you've got multiple variables all working together. So z is equal to k times x times y. And then lastly, we could have combined variation. So here's an example that I cooked up. T varies directly as the cube of r and inversely as the square root of s. Sounds like a lot. Okay, so the first thing we need to do, you can see the answer down here. I kind of work it out for you so you can see kind of my thought process. But the first part says t varies directly as the cube of r. So we do our k, and then the cube of r means r to the third. T equals k times r to the third. So that's the direct variation. Remember, it says it varies directly as the cube. The next part says, and inversely with the square root of s. So the square root of s is going to be in the denominator, and that's pretty much what we have. So that's really most of this section. So how does it work when you get into the applications? Well, let's go through just a few examples. I just want to show you how to do some of these, okay? We'll do a couple setups, and then we're going to jump into some more specific application questions, okay? Let's do question 8. This says u varies directly as v and inversely as the square of w. Okay? So what we'll do is, again, u, that's the thing that we set it equal to, varies directly as v, so we've got k times v, there's an inverse section, and inversely as the square of w. So w squared. That is going to be the solution. Let me see, right there. There you can see it. So u is equal to k times v over w squared. Let's do one more of these, and then we're going to jump into the next step in the process. So when you get these problems, you're generally solving an application question. What will happen is you won't be given a value for k. You essentially have to find it. So you are given a specific case, and then you need to solve it for a more general case. Specific solution and general solution. That's the way I like thinking about it. Let's do 12. Okay. T varies jointly. Okay. With T and R and the square of A. Okay. So now what we can do is we write our T, that's the very first thing we see. Our K is automatic. Joint variation, so varying jointly means that they're all going to be just right next to each other. So we've got TR times A, and it's the square of A. So that guy squared. It would be different if it said square root, but it says a square, so that's what we have. All right, so setting up these problems is the first part of this process. Now the second part with a lot of these is to find our value for k. Again, it's a variation constant or constant of proportionality. The way it works is this. So you'll have your setup of equation. Okay. That's what we just did. Then they'll give you a specific case. And then they'll ask you to find a general solution. Okay? So that's how a lot of these are going to work. You've got 3 steps: the setup, the specific case, the general solution. So this next one, this next question that we have, we're just going to be looking specifically at finding our value for k. That's really how it's what it's asking us. Okay, so question 18. I'm going to leave that up there so you can see it. U varies directly as V and inversely as the square root. I think you guys just got notified I got an email. Sorry about that. And u is equal to 0.04 when v equals 8 and w equals 0.04. Okay, that was a lot. So here's what we're going to do. We're going to go ahead and solve. First, we need to set up our equation. So u varies directly as v. So we're going to have k times v, and inversely as the square of w. So this is our setup of the equation, the very first step. The second step is we need to find our value for k. And this is really all we're being asked to do at this point. Oh, sorry, this should be square root. I need to make sure, sorry, I just copied it wrong. So this is going to be square root of w, okay? So now, what do we have? We're going to go ahead and substitute in u equal to k times v over square root of w. We're given the specific values, so now we go ahead and solve. So 0.04, that's our u value, is equal to k times v, which is 8, all over the square root of 0.04. Get this right? All right. Now, when you get to a step like this, you can use your device. I'm going to switch over to Wolfram Alpha and show you how to do this real quick. Go to the browser. All right. So what we're going to do is we're going to punch in exactly what we just had. So 0.04 is equal to, and I'm going to separate the top and bottom of my fraction, okay? So this is going to be k times k times 8. And then this is going to be the, you can write actually square root of 0.04. Okay? So you can write it like that. Another way to do it, if you want, you can do a caret and then do to the 1/2. It's going to be the same thing. Either way works perfectly fine. I'll just do square root because I already did it. All right, so let's go ahead and hit enter. Usually what I like doing is, again, making sure it matches exactly what I wrote down. In this case, it sure enough does. And it's funny, they don't give me any solution for k. Let me see if I can type that in. There we go. There's our solution. And wait a minute. I think they think that k is something different than what it is. Let's just do this. Let's change this to 8k. Here we go. All right. So k is approximately this. So what we get, let me go ahead and flip back to the board here. What we get is k is approximately 0.001. Okay? So if you want, if this is our specific situation, and that's going to help us find our variation constant, or the constant of variation, or the constant of proportionality, I guess is the other way of saying it. So we can actually sub that back into the original, and then that would be our final answer, 0.001 v all over square root of w. Okay. So this right here could be our final answer. I think in this one they were just asking us to find k, but if you wanted to finish it off, that would be the way that you do it. Okay. Alrighty then. Let's go ahead and do one more. That last video was a little intense and long, so I'm trying to make this one a little shorter for you. Question 24. Let me see if I can find the actual question in the book. I want to make sure I read it correctly. Okay, so it says the pressure a liquid exerts on a given point on a submarine is directly proportional to the depth of the point below the surface. So the deeper you get, the more pressure there is. Okay. If the pressure at a depth of 3 feet is 187.5 pounds per square foot, find the pressure at the depth of 7 feet. So you're probably wondering, like, okay, like what is this asking us? So first off, let's look at the setup of the question. The pressure a liquid exerts. Let's just call that, a lot of times you just have to set up your variables. So let's call this one pressure. P is equal to pressure. Pressure, if I can spell it right. D is equal to our depth. Okay. And that's really it. It's literally the pressure a liquid exerts at a given point on a submarine is directly proportional to the depth of the point below the surface. So there's no, like, by the way, little slight caveat here. I noticed this. I need to show it to you so you can really see how funny this is, okay? So let me go ahead and zoom in here. Give me just a minute. I have to show you this. This is hilarious. All right, so wrong way. 24, okay? Take a look at this word right here. The pressure a liquid exerts on a given point on a submarine. Can I ask a question? What other liquid other than water are we dealing with here? Why are we using the word liquid and not the word water? Are we submerging the submarine in, like, Jello or grape juice? Like, I think that's kind of funny. Anyway, I'm weird, I know. So, throwing that out there. All right, let's go ahead and take a look at this question then. So we've got the pressure, we've got the depth, the problem, the equation, the way it writes. Hang on, let me switch back to my correct size. There we go. We've got P, pressure is equal to K times D. So now in this question, they give us a very specific example. They say when the pressure is 187.5 pounds per square foot, the depth is 3 feet. So this is equal to K times 3, okay? Or 3K, I should say. So what this is doing is it's telling us, here's a specific case. So you can think of this as like the specific case here. All right, so we did our setup, we got our specific case, then we have to go back and find our general solution, okay? So I'm just going to change this to 187.5 is equal to 3K, okay? And then let's actually go back to Wolfram Alpha here and work on this one real quick just to find out what K is equal to. So we've got 187.5 is equal to 3K. Hit enter and make sure the input is correct. That's good. The solution is going to be 62.5. 62.5 is the solution. Okay. Let me switch back to the whiteboard. So K is equal to 62.5, which means that if I look back at this is my now general case, general solution, P is equal to that number, the K, right here, we're going to sub it in for that K, so 62.5 times D, okay? And the last thing that they ask us to do is, they're basically saying, if this is true, find it at another depth. So they're asking us to find it at a depth of 7 feet. So P is equal to 62.5 5 times 7. And I did not punch this in. Oh, yeah, I did. Okay. I did it in my notes. I'm not going to do this in Wolfram Alpha because I'm confident you can do it. This is going to be 437.5. And we need to match the units. So this is pounds per square feet. Okay. So that is pretty much this entire section. Variation, direct variation, joint variation, inverse variation, some kind of combination of all those. And so again, you find your equation, you look at the specific case to find your value for k, and then you apply it in kind of your k back into it as your general kind of formula or equation. So that's pretty much it. If anybody has any questions, again, feel free to shoot me an email, let me know. But aside from that, I hope you have a fantastic day.